Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face Trending List, published on October 29th, 2025, about 5 days ago. It shows a clear crossover. Floating point wins at coarse quantization, but for fine-grained blocks, 8-bit integer mix INT, 8 beats floating point in accuracy and efficiency, cutting energy by about 37%, and in a mixed setup, chip area by about 34%. The paper is titled INT versus SFP, a comprehensive study of fine-grained, low-bit quantization formats. And as we will see, the implications for model training and accelerator design are quite significant. Also, the author shared a GitHub repo. You'll find a Python framework to compare low-bit INT and FP formats with quantization functions and a quantized linear layer, scripts to compute QSNR, KL divergence, and perplexity, runnable examples for MXINT and NVFP variants, optional Hadamard rotation, plus eval assets and requirements. So after that overview, Table 1 lays out the low-bit format side by side. It specifies the block size for each scheme, with MX variants using 32-element blocks. NV variants use 16-element blocks, which tightens scaling and reduces outlier impact. The columns compare maximum and minimum representable values and the dynamic range, which indicates how far a format can stretch before clipping. MX formats rely on a single microscaling factor per block. The NV 4-bit formats add a second global scale to prevent overflow. Okay, Table 1 set the formats. Figure 2 shows why symmetric clipping matters for training. The dashed B-float 16 baseline stays flat, while the standard 8-bit integer range with -128 skews loss upward because gradients pile into the unique negative endpoint. Using the symmetric range with -127 removes that bias. The effect strengthens as quantization blocks get finer. So while Figure 2 highlighted why symmetric clipping stabilizes training, Figure 1 maps the full compute flow for a low-bit linear layer. The diagram shows 6 quantization points that surround the general matrix multiply, which is the core matrix times matrix operation. Forward quantizes activations and weights, then backward quantizes gradients and the transposed tensors, so every path into the multipliers carries a scaled low-precision stream. So, while Figure 1 outlined the compute flow, Figure 3 compares theoretical QSNR against crest factor, which means the peak value divided by the root mean square of a block. The plot shows that MXINT8 surpasses MXFP8 when crest factor falls below 7.55. MXINT6 only wins under about 1.96. MXINT4 overtakes MXFP4 beneath roughly 2.04. N versus INT4 can beat N versus FP4 when crest factor is under about 2.39, so smaller blocks that reduce peaks favor integers. Alright, 2 takeaways stand out. For fine-grained blocks, 8-bit MXINT8 delivers better accuracy and efficiency than floating point, while 4-bit favors floating point unless outliers are tamed with Hadamard rotation. Symmetric clipping fixes gradient bias, enabling strong INT8 training. The broader implication is clear. Co-design should prioritize fine-grained integer formats for future accelerators. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.